3 notes. You might want to have colored pencils. That might be a good idea, doing the color coding in these notes. So this section is using accumulation functions and definite integrals in applied context. So it's really a heavy dependency on the fundamental theorem of calculus part 1. So our central question then is kind of framed around that. How does the context of this question relate back to that fundamental theorem of calculus part 1? You can find the notes starting on page 10 in the packet. So let's kind of connect our past to what we want to do today. Here's our fundamental theorem of calculus part 1. We would call this the evaluation piece, or the evaluation part. And we know that the integrand here, g of t, is a rate. So we're accumulating a rate. We know that represents a change in the antiderivative. And this is the way of writing that change in the antiderivative. So g is the rate, f is the antiderivative. We start at b, we start at a and go to b as we accumulate. And so, and that's how we kind of address fundamental theorem of calculus part 1. So we're going to slightly modify this to our new tool, and really the modification is just solving for f of b. So we're using this tool in the context of we want to find an ending value given an accumulation and a starting value. So we're going to rearrange this and take the starting value to the other side by adding it. So here it is appearing on the right-hand side now, and or on the integral side, I should say. And then I just did a slight variation on the rate. We used to identify the rate as g of t. It's really, we know rate and derivative are the same thing. So I put its derivative notation. F prime of t is the derivative, and f is the antiderivative. So let's take a look at an abstract example, not something that's not tied to any context, but I'm going to give you a little bit of time to get comfortable with this model, this new tool here. So this question is: a function is known to be increasing at a rate modeled by f prime of x equals 3x plus sine x. It is also known that x equals 4, that at x equals 4, the function has a value of 15. Find the value of the function at other locations. So we know that this is our rate, or our derivative, and we know that that is our a value, and this is our f of a. So our starting point and our value at the starting point. And then let's address this first question here. What is the value? So these are finding value questions. So they'll all be that way. What is the value when x is equal to 7? So setting up our expression for finding that future value, that's our b, looks like this. With f of b, f of 7 equals the integral from 4 to 7, from our start to our end of the derivative, plus the start value of f of 4. So plugging in what we know that our derivative is 3x plus sine x. Our starting value is 15. And then today we're really going to rely heavily on using our graphing calculator to evaluate these. Just to be able to go a little quicker. I trust that you can integrate that on your own. But let's go ahead and do a math 9 from 4 to 7. 4 to 7 of 3x sine, oops, plus sine of x. Oops, I'm not sure what happened there. There we go, 3x plus, there we go, sine of x, close those brackets, and integrating that with respect to x. So I'm going to do that integration, but at the same time, I'm going to also put in that f of 4 value. There it is, 15. So I'm going to add 15 right to the end. As long as I add 15 after the dx, the calculator will interpret that as being outside the integral. So the other thing you can do is put the 15 on the front end. Okay, so we have 63.09245412. So there's our answer. So you're certainly more than welcome to write all of those digits, but we know that the standard is that College Board stops reading after the third decimal place. So we just have to decide, do we want to keep this a 2 or change it to a 3? Either is acceptable. I shouldn't say that, either is not acceptable. We have to, because if we round this, it would go round back to a 2. So the only correct acceptable answer would be 63.092. And then if you have digits after that point, that's okay. Okay, so that was a pretty standard one. We started at 4, we ended at 7. We're accumulating this area as we're sweeping to the right. We know that represents a positive region, providing if the derivative is above the x-axis. So looking at this next question then, what is the value of x at 2? In other words, b is 2. If we set up this, notice that our limits are flipped, and that's okay. It'll take care of it. We have this function here. It's not tied to any context. We don't know what this represents, but we can handle the limits of integration being flipped like this. So so we're going to go ahead and substitute everything in. So we have the integrand here, the derivative, 3x plus sin x, and then we have the starting value of 15. So if we go back, I'm going to do a second enter just to do some modifications on this instead. So I'm going to keep the 15. I'm just going to go back here and change that 7 to a 2. That's really the only thing I have to do, and hit enter. And so notice my answer is negative 3.237. So that's the answer to the second part. And again, 7 correctly rounded would stay at 7. Including any of these digits after the answer is fine as long as they're correct. But notice that because we're sweeping left, this region is now negative, and they're taking care of that negative by the fact that we kept that lower bound big and the upper bound little. Remember, you can swap these and put a minus sign on the outside too, as well. That would have accomplished the same thing. Okay, so looking at the next example, now we have some context. So now, now that kind of has an effect on if whether or not we need to modify this expression in terms of the value of the integral, whether it's positive or negative. So let's take a look at this. At time t equals 0, a tank of water begins leaking at a rate modeled by v prime of t equals minus 25 pi 10 divided by the square root of t. And v is measured in gallons and t is measured in days since the leak started. So first thing we can kind of acknowledge is that we're leaking, so we're losing water, and our rate is negative, so that makes sense that our rate would be negative if we're leaking water. No water is being added to the tank, so we don't have to worry about anything filling while it's leaking. And the tank held 24 gallons of water when t equals 2. So this is our rate. This is our starting location, t equals 2, and we have a starting value of 24,000 gallons. And I just restated that a different way so that you can see that how that we could present it in a couple of different ways. The question is, how much water is in the tank 4 days after the leak started? So the leak started at time t equals 0. So in other words, it's been leaking for 2 days by the time we figure out how many gallons are in it. So, and then we're going to look at it. We want to know how much water is in the tank 4 days after the leak started, which is 2 days after we looked into it, if that makes sense. So we want to accumulate from 2 to 4 that rate of leaking, and then we want to also consider where we started, which is 24,000 gallons, excuse me. So when we're writing this, then we're putting in this rate, we see that we have a negative sign here. So we know that with this negative sign, that we will end up with a value of less than 24,000 gallons. And before I crank that out on the calculator, So just a couple of things that, and we'll go over a question like this a little later on. Sometimes they tell you that something is leaking at a rate, but they don't put the minus sign. And so they're leaving it up to you. They're leaving it, kind of putting the ball in your court to remember to put the minus sign. Usually that would be outside the integrand here. But, if just from a contextual standpoint, if you're getting an answer more than 24,000 gallons, it's not right because you got something leaking out of this skeleton. Okay, so let's go get the answer. So we have math 9, and we're going from 2 to 4 days. And we have minus, what was that, 25 pi divided by the square root of t divided by the square root of x. And that's integrated with respect to x. And then I'm outside the integrand, so I'm going to go ahead and add on the 24,000. So plus 24,000, and we get an answer of 23,000 907. So we lost, it looks like, about over 6,000 gallons in the 2-day period. So we end up with 23,907.985 gallons at the end of that 4-day period. Again, with these decimal places here, I chose to round this to a 5. You could also leave it a 4, you can truncate. But if you round it to a 5, definitely stop writing digits. If you leave it a 4, you can put the 8 and the 8 on the end of your graph. Okay, so this is a pretty standard leaking question. They gave you the rate, they gave you the negative sign, so it was pretty much a plug and shove. And then, of course, we're at gallons here, putting on the correct units. Having a contextual problem where we know what's happening. If we have units, we should be putting units on the answer as well. Okay, so let's look at example 3. So now we're going to start testing variations on the fundamental theory of calculus. So while the last example was leaking water and they gave you a negative rate, if you look at this example, they give you a rate, and it's a printer, and it's printing documents, and it's obviously when you document to use ink. And ink, it says ink is being used at a rate of 0.2 times quantity 1 plus %. So notice no negative sign. So they're leaving it on our accord to realize that this needs to be a negative expression when we put it into the fundamental theory of calculus. And of course, if we read on here, so the printer started with the job with 5 ounces of ink in the cartridge. How many ounces of ink remaining after 3 minutes of printing? Obviously, if you get an answer that's bigger than 5, you know, just from contextually looking at that, at the problem, that wouldn't be the right answer. So that will hopefully use that as kind of an indicator too that you forgot a negative sign on the rates. Okay, so this is what we have. We have 5 ounces. We started the job with 5 ounces. That means that's our starting value. But when did we start this job? In other words, what is A? And so when we start printing, we typically refer to that as time t equals 0. So let A is 0 just from the context of the problem. We want to know what's happening after 3 minutes, so we know B is 3. So down here, okay, copied that over from the last question. B is 3. There we go. Let's get back to where we were. All right, so B is 3. And so I made up a function here. I'm calling it ink. So I want to know how much ink I have at 3 minutes. And so I'm going to invert from 0 to 3. I'm going to invert my rate. And I have to remember to make that a negative value. And then I'm going to add on my original number of ounces that I had at time t equals 0. So here comes a negative sign, and I put in the function. I've got a negative function. We know that this is going to If t is going to be positive, cosine is going to fluctuate between -1 and +1. So we know that this function itself is never going to be negative. So we definitely need the negative out here so that we can subtract what we're losing in that 3 units of printing. And then, so if we go ahead to the calculator and do a math 9 here, we're going from 0 to 3. Oops. Try that again. Math 9 to 0 to 3. And our rate is 0.2 times 1 plus cosine of t or x. That's our variable. And we are integrating, excuse me, with respect to x. Now I'll hold up here because we know I forgot something, right? Plus 5. Right, we're starting with 5 ounces of ink. So I'm going to go ahead and hit enter. This is wrong though. Okay, I just wanted to show you what's happening when you forget the negative sign. I have an answer that ends up with 5. I know it's not true because we're using ink, we should be having less as an answer. So I'm going to hit second entry real quick. I'm going to go ahead and arrow back to the beginning. I know that this rate needs to be negative, and College Board is expecting me to be savvy enough to realize that and to put in the negative. So I'm going to insert the negative sign there, and there is the amount of ink left after 3 minutes. So it's 4.3717. I kept 4 decimal places instead of 3. 4.3717. Yeah, and that would be correct because the digits are correct. Or we could round this to 4.372. And we're talking about ounces, so we'll put the units of ounces in there. Okay, so that's a variation. The variation is that I had to realize that ink is being used, so my rate should be negative. We get a couple more variations here on the fundamental theorem calculus. Up until now, we've always had a rate or a derivative to put into the integrand. Sometimes they don't give you a later derivative. Sometimes they give you a table. And of course, the only thing we can do with the table is approximate. That's the only thing that we can do that's tied to integration. So it says an oil tanker is being filled with oil. The table below has values of rates of oil being pumped over a 10-hour interval. So this is how many gallons per hour are being pumped. 2 hours into the fill, there's 150,000 barrels of oil. Use a right-Riemann sum to approximate Riemann sum approximation to estimate the amount of oil in the tanker at the start of the 9th hour. So as the 9th hour starts, that's the way we're talking about. So what do we have here? We know that 2 hours, so when A equals 2, we get 150,000 barrels, and we want to know what's happening up to t equals 9, and that's my B value. So setting up my fundamental theorem calculus, I want to know a future value at t equals 9. I'm going to accumulate from 2 to 9 my rate, but my rate is tabular, so I'm going to have to do a Riemann sum then. And I need to add on what I started with, which is 150,000 barrels. So let's take a look at that Riemann sum. It's a right Riemann sum, which means we're going to be using the right values, which means the value of 4 and 7 and 9. And so let's go ahead and calculate that. So my right RAM is going to be this interval, which is 2, times this value on the right side of that rectangle, which is 75. And then this interval is 3 wide, and that's going to be multiplied by its height, which is 75. And then the last interval is 2 hours long, and its height on the right-hand side is 70. So there's my right Riemann sum, and I think I add that up there. It adds up to 515. And so I know that this represents this entire accumulation function, all of this integration. Right? It's an approximation because it's a Riemann sum, but we're going to substitute that value in. Now look what I'm doing. I'm putting the RAM right in here instead of the 515. This for a reason, because now I'm going to tack on my initial value of 150. This is a numeric answer, right? This is a kind of a no calculator question. So this is a numeric answer. And you can leave your answer like this. Just slap on thousands of barrels and you're done. Okay, so just kind of remember those things as you're looking through your response questions. What we really need is 515 plus 150, which ends up being 665,000 barrels of oil after that 9-hour interval. Okay, so the last variation, again, we don't have a rate function, but we can also give you information in the form of a graph. Because again, we know that the area under the graph is a representation of integration. So let's get some numbers on here that are a little more legible than what you see. So we have a drone that's hovering above and moving in a vertical path. And the graph is made of 3 line segments, and it represents the velocity of the drone. So that's the rate of the change of position of the drone. And the rate is, so it's the rate of the drone that is moving straight upward over interval of time. T is measured in minutes. At time t equals 0, the drone has an altitude of 10 meters. So those are A and those are F of A. It says find, this should say drone, not the drone. Find the drone's altitude at time t equals 8. So a couple of things, just like the table in the last question where we didn't use all of the components for the sum, because we were only going from 2 to 9. This one we're only going from 0 to 8. So we are going to accumulate from 0 to 8 of accumulate the rate, which is t. And then we are going to add on our initial elevation, which is 10 meters. So looking at that region and calculating its area, we've got half 2 times 50, so 1/2 2 times 50. Plus 6, because this has a width of 6 times 50. Oops, look at that. I got another mistake. That should be 6 times 50. Hold on here, let me correct that, because that's a pretty important mistake. 6 times 50. I'm actually wrong in here. Let's call this more appropriately. This is V of T. It's V of T. T. There we go. That would be a little more appropriate representation. Let me get back to that point. There we go. V of T v 2. Now we have the correct math here. This is 300. This is 50. So I can start at 350. And I'm going to work the solution again like I did on the last example. F of, oh goodness, F of 8, not F of 9. This is what happens when you copy from one slide to the next. Okay. 8. There we go. All right. Okay, so that's that area. So again, I'm going to leave this as an expression. The integral from 0 to 8 of V of T is represented by the area of this. So that's half 2 times 50, that's 6 times 50. Doggone it. I've got a lot of mistakes on this one screen. So sorry. That should be 50. We'll get through this screen. All right. So let's get back to where we were. Okay, after 8. So I'm re-expressing, I'm continuing this expression here. So 6 times 50 plus 10. Okay, and again, that's a numeric answer. You can just draw meters on the end and leave it as such. Let's see, what do we have here? We have 50 and 310. So it looks like we have 360 meters up in the air after that 8-minute trip. Okay, so a few bumps in the road, but we eventually corrected all of our numerical answers. When we get back into the classroom, we'll go through the takeaways and head on to the test questions.